Hello, everyone. I hope you are all doing well. We are coming to chapter 5. I hope chapter 4 was interesting for all of you. In the past, we have had students not like that chapter that much. Um, so I hope everything went well with it. Chapter 5 is going to be a little more relaxed. I guess it's only 2 sections. There are not that many definitions, not that many formulas. So let's get to it. For section 5.1, we are defining what a random variable is. And that is whenever we have an event, we have certain outcomes. And each one of those outcomes is going to be a number. And we will associate a probability to each one of those outcomes. That's basically what a random variable is. Some of these questions are going to ask you for some definitions, then ask you to check if some of these are random variables with a probability distribution or not. But I wanted to show you exercise 12. So question 12, the accompanying table describes results from groups of 8 birds from 8 different sets of parents. The random variable x represents the number of girls among 8 children. Complete parts A through D below. Find the probability of getting exactly 6 girls in 8 birds. So let's take a look at the table. This is the probability distribution for x. The random variable x is the number of girls. So for each one of these 9 possible outcomes, we have a probability associated to that outcome. In this case, we are being asked to find the probability of getting exactly 6 girls. That means we want the x value to be 6. So that occurs here. So that means that the probability is 0.116. Good. Now find the probability of getting 6 or more girls in 8 birds. So now we could have 6, which we know is 0.116, but that is not the only case we are interested in because we want 6 or more. So we could also have 7. So for 7, the probability is 0.038. For 8, the probability is 0.005. Why am I adding? Remember, from section 4.2, the addition rule. When do we use the addition rule? Whenever we have an or. Why do we have an or here? Because we could have exactly 6 girls, or exactly 7 girls, or exactly 8 girls. So that or is telling me to add these probabilities. So if we add these 3 numbers, we would get 0.159 in this word. And then we're being asked which probability is relevant for determining whether 6 is a significantly high number of girls in 8 birds. So this is on the notes. Remember that if we want to find a significantly high number of anything, we are looking for that or more. In this case, it is 6 or more, which is the probability we found in part B. So it's the result from part B, since it is the probability of the given or more extreme result. And lastly, is 6 a significantly high number of girls in 8 birds? Why not use a 0.05 as the threshold for a significant event? So again, from this definition of part C, we're looking the probability of 6 or more. In this case, it is 0.159, and we compare that to 0.05. For this event to be significantly high, we would need this probability that we calculated to be less than 0.05. That is not the case. So since it is not the case, it is not significantly high. So the question is 6 a significantly high number? The answer is no. Since the probability is greater than 0.05, it is not a significantly high number. Good. I also want to show you question 16. The following table describes the results of roadworthiness tests of Ford Focus cars that are 3 years old, based on data from the Department of Transportation. The random variable X represents the number of cars that fail among 6 that were tested for roadworthiness. Is the probability of getting 3 or more cars that fail among 6 cars tested significant, determined by a cutoff value of 0.05? So we either answer yes or no. First of all, let's take a look at this table. For the first 5 rows, we have a decimal number. And here for the last 2, we have this 0 plus. Remember this 0 plus, it's 0.0000 if we round to 3 decimals, but it is not exactly 0. It's like we have 3 or 4 zeros, and then we have some numbers. So to round it, we would get something like this, but we know it is not exactly 0. Okay, so the question is the probability of getting 3 or more cars that fail significant? So what is the probability of 3 or more? So we have these. Let's add them together. We have 0.41 plus 0.005 plus 0. It is 0.046. I cannot write it down anywhere, but it's 0.046. We are comparing that to 0.05. And 0.046, it is less than 0.05. So it is significant. Okay. I hope that was clear. It's pretty similar to what we did in question 12. And lastly, I want to show you question 18. This is simple in the sense that we are just going to use one formula, the formula for the expected value. But there's a lot of information. So let's try to make sense of all of this information. When playing roulette at a casino, a gambler is trying to decide whether to bet $15 on the number 16 or to bet $15 that the outcome is any one of the 5 possibilities, 0, 0, 0, 1, 2, or 3. The gambler knows that the expected value of the $15 bet for a single number is negative $1.58. For the $15 bet that the outcome is 0, 0, 0, 1, 2, or 3, there is a probability of 5/38 of making a net profit of $90 and a 33/38 probability of losing $15. Part A, find the expected value for the $15 bet that the outcome is 0, 0, 1, 2, or 3. So we know the formula for the expected value. That is the formula for the mean of the probability distribution. I'm going to attempt to write it here to remind you all. It is on the notes. You can look at it there anyway. But this is what we do. We are trying to multiply each outcome by its probability, and then we add them all together. So notice here, the random variable is the net profit. That is the numerical value we associate to each one of these outcomes. And if we have a bet, there are only 2 possible outcomes, right? What are they? We either win the bet or we lose the bet. So if we win the bet, what is the numerical value associated to that outcome? The problem is telling me that if I win the bet, I make a net profit of $90. So that is my numerical outcome. Something important is that in some of these problems, you're going to be given a net profit. So you take that value as is. In some other problems, you will be given a total that you win. So you're going to be you're gonna need to be careful with that because you need to subtract what you pay to enter whatever lottery or bet you made so that you can find the net profit. So for instance, if we didn't have the word net profit here and they just tell us that we win $90, then the net profit is $75 because we are winning 90, but we already paid 15 to enter. So pay attention to that. So we go back to the formula. We have this outcome of 90. We multiply that by its probability. So what is the probability that we win? We are being told it is 5/38. And we do this for all the possible outcomes. We only have one other outcome. The other outcome is that we lose. In that case, we do not win any money. So we might be tempted to think that the numerical value is 0. But remember that we already paid $15 to bet. So actually, the numerical value for this outcome is -15. We consider it negative because we are losing that money. Again, we want to multiply this by its probability. And then we simply plug it in our calculators and find how much it is. We're being told to round to the nearest cent as needed. So this should be -1.18. Let's check. Perfect. I hope this was clear. And then we're being asked which bet is better. So how do we know? Well, they give us a hint. What we need to do is we need to try to compare the expected values of both bets. Because the expected value is a good mean value. It is exactly the mean value of this experiment. So we would expect to win or lose that amount of money. So whenever we have two bets, we compare the two expected values, and whichever value is higher is the bet that we prefer. So we are comparing these two expected values. The expected value we just calculated for the 5 numbers and the expected value of betting for a single number, which we are told is -1.58. So which one of these two numbers is greater? Since the expected value of the bet of number 16 is less than the expected value for the bet that the outcome is 00, 0, 1, 2, or 3, the bet on 0, 0, 0, 1, 2, or 3 is better. And remember, these are negative numbers, so if we just compare 158, 118, 158 is greater, but these are negative. So it's kind of like the opposite. If you struggle with this, maybe you can draw a real line, find the two numbers, and whichever is to the right, most to the right, that is the greater number. Okay, I think that's all I wanted to show you for section 5.1. I'm going to stop sharing for 1 second. Just to open the assignment for section 5.2. And in 5.2, what we are doing is discussing a more specific random variable or probability distribution. Let me share my screen. I have it right here. Wait. That is not quite the way I wanted to share it. Give me 1 second, please. The good thing is you can just skip this in the video. Okay. So as I was saying, chapters 5 and 6 both deal with probability distributions. In chapter 5, we will discuss discrete distributions specifically. And in chapter 6, we will discuss continuous probability distributions. And in section 5.2, we will discuss specifically the binomial distribution. So that means that we will not be given a table. We have a formula to find all of these probabilities, so we will be asked to calculate those on our own. So I want to show you a few exercises from this one. Let's take a look at 14 first. Multiple choice questions, each have 4 possible answers, A, B, C, and D, one of which is correct. Assume that you guess the answers to 3 such questions. Use the multiplication rule to find the probability of WCC, where C denotes a correct answer and W denotes a wrong answer. It's very important to know that the order of all of these matter. So it's not the same event to do wrong, correct, correct, than to do correct, correct, wrong. Maybe the probability is the same, the number, but the events are different. Okay, so what is the probability that we get the first question right? No, sorry, the first question wrong, and the second and third questions right. Well, we know these are independent. We can use our multiplication rule we learned in section 4.2. So we multiply the probability of getting the first answer wrong, and then the probability of getting the second answer right, and the probability of getting the third answer right as well. We know these probabilities will be fractions. What is the probability that the first answer is wrong? We have 4 possible options, A, B, C, or D. We know 3 of them are wrong. And with the same logic, there is only one correct answer in the second question and one correct answer in the last question. We multiply the fractions, we should get 3 over 64. Let me make sure. Okay, so that looks good. Excellent. Beginning with WCC, make a complete list of the different possible arrangements of 2 correct answers and 1 wrong answer. Then find the probability for each entry in the list. So we have WCC, that is 3 over 64. CCW, same idea. We want to multiply these 3 probabilities. So the probability of getting a correct one is 1/4 times 1/4 times 3/4. We know this is the same number we had before. So it is 3 over 64. We notice we got the same number, but the calculations to get there were a little different. And we'll get something similar for this last one. So correct is 1/4, wrong is 3/4, correct is 1/4. So that is 4 over 64. Based on the preceding results, what is the probability of getting exactly 2 correct answers when 3 guesses are made? So this is important, and this is why we have a combination on the formula for the binomial distribution. Because we are choosing all the possible outcomes where we have 2 correct answers and 1 wrong answer. We can see there are 3 of them. So we have 3 cases. We either got the first one wrong, that is 364, or that's plus. We get the second one wrong, that is 364, or we get the last one wrong, that is also 364. So if we add all of these, we get 9 over 64. And this is the probability that if we guess in 3 questions, we get 2 correct answers. Okay. Good. I want to show you question 18 as well. Based on a poll among adults who regret getting tattoos, 21% say that they were too young when they got their tattoos. Assume that 6 adults who regret getting tattoos are randomly selected. and find the indicated probability, complete parts A through D below. Find the probability that none of the selected adults say that they were too young to get tattoos. So we use the formula. Let me see if I can show you that very quickly. It's on the notes, but maybe it's good that you look at it right now. So this is the formula we are using, okay? We have a combination. Remember, N is the amount of experiments we do, the amount of trials. In this case, it's 6 because we have 6 different subjects. And we are asked to find the probability that none of them regret their tattoos. So that means that X is 0. We are given the probability of an adult regretting getting their tattoo, or maybe they got it too young. So that is 0.21. And we know that Q is the complement of P. So that is 1 minus 0.21. So this is the formula that we're using, okay? So let's go back. First, we have the combination out of 6 adults. We want that none of them think that they were too young to get tattoos. So that is X equals 0. And then we multiply by the probability that someone think they were too young. We raise that to 0. And then we have the complement, which should be 1 minus 121 raised to n minus x, which in this case is 6. So let's plug this in and find the probability. We are asked to round to 4 decimal places. See what I got? Perfect. Part B, find the probability that exactly one of the selected adults say that he or she was too young to get tattoos. Same formula. Now X equals 1. So we have N equals 6. That remains the same. Now X equals 1. So this changes, this changes. Probability P is the same. Now this is raised to 1, so this changes. And 0.79 is raised to n minus x, so 6 minus 1, 5. So same formula. Now X equals 1. Let's find this probability. So we plug it in our calculator. We round to 4 decimal places. I think we should get 0.3877. Got it. Part C. Find the probability that the number of selected adults saying they were too young is 0 or 1. So again, the key here is OR. That OR is telling me that I need to add these 2 numbers up. So I do 0.2431 plus 0.3877. I should get 0.6308. And last one, if we randomly select 6 adults, is 1 a significantly low number who said that they were too young to get tattoos? So remember, what we do is we compare this probability to 0.05. We always want it to be 0.05, but now that it's significantly low, we do 1 or fewer. So we want to compare the probability of 1 or fewer with 0.05. For this to be significantly low, the probability of 1 or fewer is less than or equal to 0.05. In this case, this is much greater. So the answer is no, because the probability that at most one of the selected adults say that they were too young is greater than 0.05. Here with the options for at most one, maybe it gets a little tricky. Like greater than or at least. So we need to pay attention to that as well. And there is one final exercise I want to show you, which is question 29. Okay, so here we have an experiment. Mars Inc. claims that 20% of its M&M plain candies are orange. A sample of 100 such candies is randomly selected. Find the mean and standard deviation for a number of orange candies in such groups of 100. So remember that for in section 5.1, we learned a general formula to find the mean and the standard deviation, but it was kind of complicated. In the binomial distribution case, the formulas simplify a lot. So now the formula for the mean is simply n times p. So let's identify that. In this case, we have 100 experiments. So that is n, 100 trials, n equals 100. And the probability is 0.2. So if we multiply the two, we get that the mean is 20. It's either A or B. And for the standard deviation, we will first find the variance. So for the variance, again, the formula is very simple in this particular case for a binomial distribution. The formula for the variance is n times p times q. Again, that is on the notes, so you can take a look at that. But in this case, we know n is 100. We multiply that by p, which is 0.2. And then we multiply by q. Remember, q, it's the complement, so it's 1 minus p. So 1 minus 0.2, that is 0.8. And we get 16. That is the variance. But we are being asked to find the standard deviation. So how do we find the standard deviation? If we have the variance, we simply take the square root of that. That's it. You can still use the general formulas to find the mean and standard deviation for a binomial distribution, but don't. It's going to be way more complicated, way longer. It's going to take more time. There's more room to make mistakes. So let's just use the simpler formulas. Okay. I think that's it. I hope this was helpful. If you have any questions, please reach out and I'll be happy to help. So have a good one, guys. Bye.